all of you. Today we are going to start the new topic, that is the solution topics. We have completed one topic of the physical chemistry, that is chemical kinetics. This is the second topics of the physical chemistry, that is the solution. We know that the solution is the what? When solute is mixed in the solvent, then there is a formation of the solutions. So these two quantities are key for the formation of the solutions. Solute are always present in the small portions compared to the solvents. Solvent are always present in the maximum proportions compared to the solute. And the solute can be mixed in the solvents, so there is the formation of the solutions. So condition for the formation of the solution is that solute are to be dissolved. For best example is for understanding the solution is a mixture of the sugar in the waters. So in this case we can consider the sugar as the solute which is present in the small quantity, and the second one is the water. Water is considered as the solvent and it is present in the maximum quantity. So when solute, that is the sugar, is present in minimum quantity, means it can be easily mixed, dissolved in the waters and form the solutions. But if it is present in the maximum quantity, for example, if you are taking the 2 grams of the sugars and mix in the 5 ml of the waters, the 2 gram of sugars can be easily mixed in the 500 ml of waters. So form the solutions, means the solute is in the small quantity and solvent in the sufficient maximum quantity. But if you are taking the solute in maximum quantity, means you are taking the 500 grams of the sugars and 100 ml of the waters. So it cannot be mixed, means we cannot form the solutions. So the quantity is also most important. Though, so explaining these concepts, so we will understand the solutions. The solution is defined as the homogeneous mixture. Solution is defined as the homogeneous mixture. Homogeneous means looking same. No, there is a formation of any phase. Only one phase is there, not two phase they there. Only one phase formations means the uniform liquid formation. And generally waters mix in the water and the sugar solution is always uniforms. Water and the salt mixture solution is the always uniforms. Water and oil is non-uniform, form the two phases. So for the solutions, the condition is that the homogeneous mixture of the two or more substances having the uniform properties, throughout which the concern of the single phase, means a single phase formation should be there. So we can say it as the solutions. Otherwise it cannot be solution, it will be give the other names, that is suspensions or colloidal solutions, colloidals. Okay, so for the solutions it must be the single phase, that is homogeneous. Next one is the solvent. The components of the solutions which constitutes a larger part of the solutions, the component of the solutions which constitute the larger part of the solutions called as the solvents. So we understand it very well by giving the example of the water and the sugars. So solvent is the water, it should be present in the larger part of the solutions. Next one is the solute. The component of the solutions which constitute the smaller part of the solutions, the component of the solutions which constitute the smaller part of the solutions is called as the solute. The component of the solution which constitute the smaller part of the solutions is called as the solute. Next is the binary solutions. The solutions which contain two substances or components is called as the binary solutions. The solution which contain two substances or components is called as the binary solutions. Binary liquid solutions. Both components are present in the liquid states are called as binary liquid solution. Type of the binary liquid systems. So there are three types of the binary liquid systems, and these three types are: one is the completely miscible liquids, second one is the partially miscible liquids, and third one is the completely immiscible liquids. So first is the completely miscible liquids. The example is the water and alcohol, benzene and the toluene. These are the completely miscible liquids, and example of the solutions. Completely miscible liquids is the water and the alcohol, benzene and the toluene. Next one is the partially miscible liquids. So in the partially miscible liquids, phenol and the water and triethylamine and waters. Phenol and waters, triethylamine and water. This is the partially miscible liquids. Third one is the completely immiscible liquids. Completely immiscible liquids, in that iodobenzene and waters, benzene and waters, iodobenzene and water, benzene and water. This is the completely immiscible liquids. First one is the completely miscible solutions. To completely miscible solution, when two components are completely miscible with each other in all proportions, they give two types of the solutions. A is the ideal or the perfect solutions. Second is the non-ideal or the real solutions. If the completely miscible solutions are there, then it having the two types. One is the ideal or the perfect solution. Second one is the non-ideal or the real solutions. So next point is that the thermodynamics of the ideal solution. What is the thermodynamics of the ideal solutions? So the ideal solution and the Rawls law. Thermodynamics of ideal solutions, in that we are studying the ideal solutions and the Rawls law. So considering the solutions containing the components A and the component B, these are the two components which form the solutions. So both the components are volatiles, means then can be easily evaporates. It is called as volatiles. If you understand best, you know that ether is the best volatile. Ethyl alcohol, it is the best volatile. So the materials should be volatiles, and form the ideal solutions. Let consider the PA, pressure of A, be the partial vapor pressure of the component A, and PB, the pressure of B, means the partial vapor pressure of the component B, because the volatile components having the some partial vapor pressures, because it removes easily, means it having the some pressures. So when the vapors and the liquids phase are at equilibrium, means the continuously converting into the liquid, into the vapor into the liquid. So when the vapor and the liquid phase are at equilibrium, according to Dalton's law, total pressure P is equal to sum of the partial pressure. According to Dalton's law, total pressure P is equal to sum of the partial pressures. Mean total pressure P is equal to partial pressure of A plus partial pressure of B, because they are in the solution forms. We form the solutions containing two components A and B. So total pressure is equal to partial pressure of A and the partial pressure of the B. If XA and XB are the mole fractions, XA and XB are the mole fraction of the components in A and in B, the vapor mixture, then vapor pressures PA, partial vapor pressure of A, is equal to partial vapor pressure of the fraction of A, and partial vapor pressure of B is equal to partial vapor pressure of the fraction B. So PA standard pressures of A is equal to P into A, and P standard partial vapor pressure of the B is equal to P into B. So by definition, an ideal mixture, that is the one in which both the components obey Rolle's law over at entire range of the composition at all temperatures. By definitions, an ideal mixture, that is one in which the both components obey the Rolle's law over the entire range of the compositions at all temperatures. So the Rolle's law statement is that it states that the vapor pressure PA of any solvent A, state that the vapor pressure PA of any solvent A is equal to its mole fraction XA, equal to its mole fraction XA in the solution, multiply by the vapor pressures P standard A of the pure solvents, P standard for the pure solvents at the same temperatures. So the mathematically vapor pressure of the A, partial vapor pressure of A is equal to mole fraction of A into vapor pressure of pure A, whereas the PA and PP are the vapor pressure of the solvents A and B, solvent B respectively, and the P standard B is equal to vapor pressure of the pure component A and B respectively. So the variation of the partial pressure, partial and the total vapor pressure with the composition of the liquid mixture at the constant temperature is shown in the figures. So the diagram, it is represented by the vapor pressure of the A and vapor pressure of the B and total vapor pressure of the system, that is P is equal to vapor pressure of A plus vapor pressure of B. It is always high compared to vapor pressure of A and vapor pressure of B. Both are interchanging. Partial vapor pressure of the liquid A and partial vapor pressure of liquid B are clearly mentioned in the diagrams. So one side is the mole fraction, another side is the vapor pressure. Okay, as the mole fraction increases and the vapor pressures also increases, so we will get the diagrammatical representation, graphical representation of these two. So the plot of the partial vapor pressure of each component against its mole fraction is straight lines passing through the origins. The graph indicate that the plot of the partial vapor pressure of each of the component against its mole fractions is a straight line passing through the origins, means as the mole fraction increases, partial vapor pressure is also increases. That's why it is a straight line from the origin. So total vapor pressure is the sum of the partial vapor pressure is also a straight line when xb is equal to 1 and xa is equal to mole fraction of b is equal to 1 and mole fraction of a is equal to 0, means the a is absent, only one liquid is there. The total vapor pressure is the sum of the partial vapor pressure is also a straight line when xb is equal to 1, that is solution contain any pure component B. Then the partial total pressure xa, total pressure is equal to mole fraction of A into partial vapor pressure of pure A plus mole fraction of B into partial vapor pressure of pure B. Here is the A is absent, so it is written as the 0, only remain is the 1 into partial vapor pressure of pure B. So total pressure is equal to partial vapor pressure of pure B. So when XA is equal to 1 means the mole fraction of A is equal to 1 and mole fraction of B is equal to 0, that is solution contain only pure component, then partial total pressure is equal to partial vapor pressure of A plus partial vapor pressure of B, but partial vapor pressure of pure B is 0, so the finally it becomes 0 and only one component is there, that is the partial total pressure is equal to the partial vapor pressure of pure A. So this can be easily easily derived. So in the next lecture we will discuss the next part, that is deviations from the Rolle's law. In the deviations we are going to study the non-ideal solutions. So the friends, to practice, remind the organic chemistry reactions, practice it. Always remind that organic chemistry is volatiles. If you not practice, then you cannot remind or you cannot memorize this. So do the practice to memorize and attend all the lectures. Thank you very much.